أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. I welcome you all in the online session of power generation class. Hopefully you all are fine and having good health. Today the topic of our lecture is chapter 3, gas turbine power plant. How does a gas turbine power plant work? The main equipment, the gas turbine function is the same way as internal combustion engine. It sucks in air from the atmosphere, compresses it, the fuel is injected and ignited. The gases expand, doing work, and finally exhaust outside. The only difference is instant of the reciprocating motion. Gas turbine uses a rotatory motion throughout. The main components of such system can be briefed as below. In this slide, you can see the working principle of number one section, that is the compressor. The compressor sucks in air from the atmosphere and compresses it to pressure in the range of 10 to 20 bar of pressure. The industrial unit of pressure in a steam turbine is bar. The compressor consists of a number of rows of blades mounted on a shaft. This is something like a series of fans placed one after the other. The pressurized air from the first row is further pressurized in the second row, that first row to second row, and so on. Stationary veins between each of the blade veins is in between the blades cross guide the airflow from one section to the next section. The shaft is connected and rotates along with the main gas turbine further from this section to this one. So this is the functionality of compressor. Combustor. This is the annual chamber where the fuel burns and is similar to the furnace in a boiler. The air from the compressor is combustion air burns arranged circumferentially on the annular chamber control the fuel entry to the chamber. The hot gases in the range of 1400 degrees centigrade to 1500 degrees centigrade leave the chamber with high energy levels. The chamber and subsequent sections are made of special alloys and designs that can withstand this high temperature. Now, moving towards the third section, that is turbine. As you can see here, the turbine does the main work of energy conversion. The turbine portion also consists of rows of blades fixed to the shaft. The stationary guide vanes direction direct the gases to the next set of blades. The kinetic energy of the hot gases impacting on blades rotates the blades and the shaft the blades, and vanes are made of special alloys and designs that can withstand the very high temperature gas. The exhaust gases then exit to exhaust system through the diffuser. The gas temperature leaving the turbine is in the range of 500 degrees centigrade to 550 degree centigrade. So these are the turbine section which I give you the idea that how it works. Up till now, if you have any kind of question or query, please feel free to ask. I will answer your question or resolve your query. If you have any kind of question, query, Up till now, please feel free to ask. Otherwise, I continue the session. So, I was discussing about the turbine section. Now, moving towards the fourth part, that is generator. The gas turbine shaft connects to the generator to produce electric power. And generator it is placed at the end of well, uh, turbine section. This is the similar to generators used in conventional thermal power plant. So please read these two things and ask if you have any kind of question or query. So hopefully all things are clear. Now moving toward the next slide, that is the auxiliary system. The three main sections of a gas turbine are the compressor, combustor, and turbine. The gas turbine power plant has to work continuously for a long period of time, which means 24 hours in a day and 7 days in a week. Continuously, it works output and performance deadline. Apart from the main sections, there are other important auxiliary systems which are required for operating a gas turbine power plant on a long-term basis. Now moving towards the next section, that is one air intake system. In our gas turbine or gas system turbine based power generation system, air intake system provides clean air into the compressor. Into the compressor. During continuous operation, the impurities and dust in the air deposits on the compressor blades. We all know these things. This one is the problem. This reduces the efficiency and output of the plant. The air filter in the air intake system prevents this. A blade cleaning system comprising of a high pressure pump provides online cleaning facility for a compressor blades. The flow of large amount of air into compressor creates high noise level. A silencer in the intake duct reduces the noise to acceptable levels. That a particular silencer that is available in most of the vehicles. Same phenomena can be followed in this air intake system. Now, moving toward the second part, that is the exhaust system. Exhaust system discharges a hot gases to a level which is safe for the people and environment. The exhaust gas that leaves the turbine is around 550 degrees centigrade. This includes an outlet stack high enough for the safe discharge of the gases. Silencer is an outlet stack reduces the noise to acceptable levels, because sometimes noise would be irritable. In combined cycle power plants, combined cycle is a unique kind of power plants. The exhaust system has a diverter damper to change the flow of gases to the heat recovery boilers instead of the outlet stack. Number third section is starting system. Starting system provides the initial movement of the gas turbine to reach the operating speed. This is similar to the starting motor of your car. The gas turbine in the power plant runs at 3000 rpm for the 50 Hz grid and 3600 rpm for 660 Hz grid. This is the main phenomenon which the 50 Hz and 60 Hz turbine system works. During starting, the speed has to reach at least 60% of the turbine to work on inertia. The simple method is to have a starter motor with a torque converter to bring the heavy mass of the turbine to the required speed for large turbines. This means a big capacity motor. The latest trend is to use the generator itself as the stator motor with suitable electrics. In situations where there is no other startup power available, like a ship or an offshore platform or a remote location, a small diesel or gas engine is used. Now, coming towards the fourth section, that is the fuel system in gas turbine power system. The fuel system prepares clean fuel to burning in the combustor. Gas turbines normally burn gas or natural gas but can also fire diesel or distillated fuels. Many gas turbines have dual firing capabilities. A burner system and ignition system with unnecessary safety interlocks are the most important items. A control valve regulates the amount of fuel burned. A filter prevents entry of any part- particle that may clog the burners. Natural gas directly from the wells is the scrubbed and cleaned prior to the admission into the burner turbine. External heaters heat the gas for better combustion. For liquid fuels, high pressure pumps pump fuel to pressure required for fine automation for of the fuel for burning. In this figure, you can see the air intake section can get the air in this way to place that particular air for the inside of the power plant. Starting unit can be available there, that is the placement of generator. And the air inlet in the side, particularly the outlet stack is air, silencers is also available here to reduce the noise. Auxiliary system in the gas turbine power plant system, you can see the exhaust system can get the aromatic gases from the outlet stack, and the diverter damper is also placed there. The flow of HRSG in a combined cycle plant placed here. In this section of turbine, you can see a heater, filter, and control valve also available to adjust the required fuel gas from this way to inlet in the primary and secondary subsections of turbine. At the end, the common shaft, which is coupled with the generator, can turn the generator from this way to produce electricity and provide the supply to transformer further. From this section, the third part is isolating of gas turbines. The same gas turbine performs differently in the high altitudes of La Paz, Bolivia, and tropical island of Singapore. These are placed here, and it performs differently in winter and in summer in Saudi Arabian deserts as well. This has to do nothing with a gas turbine itself, but is due to ambient atmospheric conditions. Atmospheric condition ambient means the permissible limit of temperature that is normal for a device or system. For example, the manufacturer's brochure promises a machine capable of 100 megawatt. This is the claim that is produced by a company. Output at an efficiency of 35%, but actual performance is different. We all know this thing, the practical scenario can be changed as declared. This is not due to the fault of a machine, but because of different ambient conditions. Because the Saudi Arabia is having different environmental conditions, and the Singapore tropical island have different weather conditions. So plant cannot be worked in different kind of weather condition in same declared scenario, so it can be versatile in level. This is not due to the fault of ambient machine but because of the different ambient conditions. To eliminate such misunderstandings, the gas turbine output and performance is specified at standard condition called the ISO ratings. These are specified as per ISO standards that are 3977-2, and these are the standards of gas turbine procurement Part 2 standard reference conditions and ratings. These are the standardization on which we have to understand that claim by the ISO standardization number. The standard conditions are explained below that ambient temperature, relative humidity, and elevation. The three standard conditions specified in the rating are ambient temperature, that is 15 degrees centigrade, relatively humidity 60% ambient pressure at sea level. These conditions affect the air density. How does air density affect the gas turbine output and performance? The compressor suction in a fixed volume of air for each rotation of the blades. The mass of the air depends on the air density, so at sea levels, on rotation sucks in more kgs of air than at place at high altitude. The work done by the gas turbine, as an example, the heat energy to mechanical energy conversion depends on the mass of the hot gases, the specific heat and temperature difference. The mass of the hot gases depend on the mass of the air that is taken in. This means at sea level the gas turbine gives more output than at high altitudes. Number two section is inlet and exhaust losses. The standard conditions specify that inlet and exhaust losses is zero. The intake system and the exhaust system offer resistance to the flow of air and exhaust gases. The energy to overcome these resistances comes from the gas turbine. This reduces the net output of the gas turbine. The configuration and layout of the intake and exhaust systems varies from plant to plant because single plant have not a capability to achieve the similar plants. Every kind of plant of manufacturing, environmental conditions, and part of components tell its different kinds of possibility of processing. According to the losses, these losses reduces the actual output of gas turbine from the rated value. Number three has the suction-based load operation at 100% rated power. The standard consideration that the gas turbine operates at 100% rated load. The efficiency quoted at the standard ratings are for this 100% load. Efficiency of the gas turbine at part load operation is different from that at 100% load. If you buy a machine rated at 100 megawatt, the operate at 75 megawatt, you will not get rated efficiency. The performance of the plant operating as a base load plant is different than a peaking load plant. This is mainly due to the frequent starts and stops that lead to iteration of the performance. Now, number four section tells us the corrections. All the manufacturers provide correction factors for deviations from the various standard ratings discussed above. If the actual conditions are known, the output and efficiency at the standard ratings is corrected to the actual conditions. Consider these corrections when specifying, purchasing, and operating reading gas turbine power plants. Understanding of the ISO ratings and the actual plant conditions is essential when specifying and buying a gas turbine. Also, this can be used to compare the performance of gas turbines, which we understood easily. Chapter 3 Gas Turbine Power Plant Theoretical Analysis comes there. Up till now, if you have any kind of question or query, you may ask and feel free to ask. I will answer your questions and resolve your query. If you have any kind of question, please feel free to ask. Hopefully, there is no kind of query, so I continue the session. So, Breton cycle. The ideal cycle for gas turbine is Breton cycle, also known as Joule cycle. This ideal cycle is a closed type using perfect gas as working fluid, where specific heat is assumed constant. The simplified schematic of the Breton cycle can be seen in this figure. It consists of two parts, the open cycle and Breton cycle as closed system. Open cycle, you can see there is not an exchange heat chamber there, which means the air intake in compressor and going through from the combustion chamber. Air is inlet in the combustion chamber to burning out the fuel and to produce its process to generate the output and then provide the output to a form of steam in turbine, and the product further will be formed that can be going through from the condenser. Further, the network output can be formed. This is the open cycle, and in this cycle you can see the B section called baritone cycle, a closed loop system. Same scenario is available there. The two are same, that compressor can compress the air and the heat exchanger exchange the heat, provide the output to turbine. And similar scenario in the loop form, get the heat from the turbine to convert it heat exchanger and provide to compressor, and the cyclic process repeat and repeat again. This heat is in inlet and this one is outlet. The result is formed in the network out from this way. Then the baritone cycle comprises in four parts. As you can see, these are mentioned follows. Number one, ambient air is drawn into compressed compressor and brought to the higher pressure. Also increase its temperature. This required work input, that means Wn. Because it is a work required, we want this value to be as small as possible, the input work. Number two section is the high pressure air then proceeds to the combustion chamber where our fuel is mixed with the air and combusted. This is modeled as constant pressure heat addition that Q in. In our third section, the resulting high temperature gases enter the turbine where they are expanded to a lower pressure. The turbine extracts work from the fluid W out, producing a torque on the shaft that is connected to the compressor. The work created by the turbine needs to be only large enough to drive the compressor and auxiliary components. The same cyclic process can be fulfilled here. You can see the ambient air can be perform the input work from this section in power of input in compressor and then provided to the heat exchanger in section 2, and then it fulfill its output, provide output to the turbine P out, which we discuss in this section. Then number 4, the cyclic process can provide its output to the cooler. During this whole cycle of baritone, the load is driven by this cycle from 1 to 4 and 4 to again repeating cycle. Finally, when modeling this as a closed cycle, the exhaust gases can be modeled as a constant pressure heat rejection. Up till now, if any one of you have any kind of question or query, please feel free to discuss. I will answer your question and resolve your respective query. Up till now, if you have any kind of question or query, please raise. This section is limited to this time, and we have to end today's session. Hopefully, all the things are clear in your mind, and there is no kind of query or question from your side. So, we end today's session with this lecture. Allah Hafiz.